Alright, so lecture 16 on transform of discontinuous and periodic functions. So we're going to go back to take a look at something called step functions. So we have one example when we talk about finding Laplace transform of piecewise defined function, and more specifically the unit step functions. So we're going to go back and take a look at that and how you do or manipulate any algebraic things on the unit step function. And later you're going to determine Laplace transform and inverse Laplace transform on functions using the shifting functions technique. And we're going to talk about periodic functions and evaluate or finding Laplace transform and inverse Laplace transform of periodic functions. So the unit step functions, you have seen that again in lecture 14 when we try to find Laplace transform of piecewise defined functions. So unit step function is of the form u of t equal to 0 when t is less than 0, and when t is greater than 0, the function is equal to 1. This again called the unit step functions or Heaviside function. Heaviside is an English mathematician who come up with this function. And the picture for the unit step function is illustrated here. So this is unit step functions. So for the unit step functions, of course, you can translate it, you can move it to the left, you can move it to the right. It depends on the need of the problem. Right? So the shifted unit step function is written as u sub c of t. For c is the amount that you want to move, right? Let's say you want to move to the right by 2 units, so c is equal to 2. If you want to move it to the left, well, c is also equal to -2. Not only that, you have notation of u sub c of t. You can also write this function as u of t minus c. Okay. Now, because of the Laplace transform that we are working with, we are just interested in c is greater than or equal to 0 only, right? So that's why you have u of t minus c. So the minus c here is that you move to the right by c units. Right? So this is the shifted unit step functions. Alright, the notation again is u sub c of t or u of t minus c. Why minus and move it to the right? You can think of this as, daylight saving. When you move the clock forward, you lose some sleep, right? So that's why you have u of t minus c. And when you translate it to the left, when you move the clock backward, you gain some sleep. Right? Remember that. So when you move the functions to the left, you have u of t plus c. Something like that. And here, this is you move the entire unit step functions to the right. So that's you have shifted unit step function, and the function is going to be u of t minus c. Okay. Now you can also manipulate this unit step function or shifted unit step function as followed. So if you have the function f of t equal to 1 minus u of t minus c, right? So the function u of t minus c is equal to piecewise defined functions of 0 when t is less than c is equal to 1 when t is greater than or equal to c. You can do manipulations here, that is 1 minus 0 for this interval of t less than c, and 1 minus 1 for the interval of t greater than or equal to c. So 1 minus 0, you have 1 for t less than c, and 1 minus 1 is equal to 0 for t is greater than or equal to c. So when you manipulate this shifted unit step function, this is the step functions that you're going to get. Okay, so this is also the shifted unit step function, but in different form. You can also compress this, extend that to whatever the need that you want for the functions. So you have this functions right here. This is the shifted unit step functions, and this is equal to u of t minus 2 because you shift it to the right by 2 units, or this is u sub 2 of t. And you can make this functions a little bit bigger. Instead of the functions like the horizontal line at 1, you can move that to the functions to the horizontal line at 2. And this is the function 2 times u of t minus 2. So u of t minus 1. Or this is 2 times u sub 1 of t. Something like that. So you have unit step function, you can translate it, or you can shift it to the left, shift it to the right. You can manipulate it to whatever you want. Okay, and this is very useful. This type of functions can represent the signals that you get in reality. Right? So let's think about this type of function, the unit step functions, in terms of the signal that you get for your computer or your any machine that you get, that the computer get the informations based on 0 and 1. Right? So 0, 1 here, it's just how the computer communicates. Right? You can also think about when you have a more complicated signals. Let's say you have the signal related to traffic lights. Right? Right, let's say the red is 0, green is, let's say 1, and the yellow light is 1/2, or something like that. It depends on the time interval. You have the signal as red, or you have the signal as green, or you have the signal as yellow. Okay. So those type of signal occur around us a lot, and it can be represented using the unit step function or the shifted unit step function. That's just a quick introduction to the unit step functions. Sometime when you get more complicated functions, for example, periodic functions that you're going to see later, instead of working with periodic function for the interval from -infinity to +infinity, you can just use part of the periodic function. It's called the window functions, and the window functions will be based on the unit step function or the shifted unit step functions to work with. Right? So you just look at a small window of functions and then translate or copy that to the entire periodic functions. So it's very convenient for us to understand this unit step function, shifted unit step function, and later the window function. Then we can work with periodic functions. All right. So I have this piecewise defined functions. I want to sketch this graph of the function and then express the function in terms of shifted unit step function or step functions. All right, so you have 4 different intervals here corresponding to 4 different functions. Right? So in the interval between 0 and 4, the function is 2. In the interval between 4 and 7, the function is 5. In the interval between 7 and 9, the function is -1. And when t is greater than 9, you have the functions to be 1. Okay, I'm going to plot this. So between the intervals 0 and 4, so 0 here, 1, 2, 3, 4. Okay, and the function is 2, so 1, 2. Okay. So you have t is greater than or equal to 0, so you have a closed circle here at t equal to 0, and an open circle at t equal to 4 for the functions of t equal to 2. Then between the interval 4 and 7, 4, 5, 6, 7 here, the function is 5. So the function is 3, 4, 5. So here, 4 to 7. So t is greater than or equal to 4. You have closed circle here, open circle here. Between 7 and 9, when t is greater than or equal to 7 and less than 9, the function is -1. So here, function is -1. Closed circle here, open circle here. And when t is greater than or equal to 9, the function is 1. So right here with the closed circle. So this is the graph of this piecewise defined function. Now what you do is that, can you express this function in terms of the shifted unit step function? Okay, and see what happens. So here's the procedure. You're going to see this approach over and over again in this lecture notes. Right, to get the final answer of the function that, or the shifted unit step function that represents this piecewise defined function, here's the following procedure. You're going to start out with the first functions, obviously, and the first function is in the interval start at 0. Therefore, you get 1t is going to be 2 times u of t. Right. U of t indicate that this is the unit step function, not shifted unit step function. This is this unit step function. All right, so f2t is going to be, you're going to look at, right, so you start with 2, right? Now you add to that, so 2 times u of t. Now what is the next function? The next function is at 5, right? F of t equal to 5 in the interval between 4 and 7. So you start here, right? At 2, you're going up by 3 units, so 1, 2, 3. Because you're going up, you do plus 3 times u of t minus 4, because you shift this functions to the right by 4 units. You follow the idea? All right. Now, another way to look at number 3 is that instead of counting from 2, go up to 5, what you do is, this is a more general formula that you can use for all the cases. So instead of counting, what you can get here is, this is equal to the function, the new function, minus the old function. Okay, so f new minus f old. So the new function is 5 minus the old function is 2. So that's why you have the coefficient 3 in this case. Okay. So now that's the second step. Now the third step is to look at the third function, which is -1. The third function should include all the informations that you got previously. So 2 times u of t plus 3 times u of t minus 4. Now you get -1. So remember, you are at 5. You go down to -1, so 5. Go 1, 2, 3, 4, 5, 6. You go down by 6 units. That's why you got -6 times u of t minus 7. Why 7? Because you shift the functions to the right by 7, right? And because the interval starts at 7 as well. Again, you can count that, how many times you move the function down, right? So in this case, you move it down by 6 units. Or you can look at this by using the formula. So you can get, so instead of counting, this -6 is equal to f new minus f old. So in this case, the new function is -1 and the old function is 5. So that's why you get -6 for the coefficients. Okay, now for the last function, which is 1 in the interval from of t is greater than 9, greater than or equal to 9. So you start here as -1, you move up by 1, 2 units, and therefore f4 of t is going to be 2 times u of t plus 3 times u of t minus 4 minus 6 times u of t minus 7 plus 2 times, because you move up by 2 units, of u of t minus 9. Again, the 2 is that you can count, right? You start at -1, go up by 2 units, so that's why you get 2. Or again, you can consider this as the formula of f new minus f old, and the new function is +1 minus the old function is -1. So 1 minus -1 give you 2. So that's why you have the coefficients 2. And this is the function that you're looking for, right? To represent the piecewise defined functions that we have here. Or in other words, the piecewise defined function can be represented using the unit step function and the shifted unit step functions. You're okay with this calculations, right? So this is the function that you're looking for, or the function. Let me conclude that f of t is equal to 2 times u of t plus 3 times u of t minus 4 minus 6 times u of t minus 7 plus 2 times u of t minus 9. Okay, so that is the functions that you're looking for. Now, sometimes when the interval starts at 0, t is greater than or equal to 0, that is the unit step function, and sometimes they do not write down u of t, they just write down a constant 2, right? And this still represents the functions that you're looking for. So 2, which is the first function on the list of the piecewise defined functions. So 2 plus 3 times u of t minus 4 minus 6 times u of t minus 7 plus 2 times u of t minus 9. So either one should be fine, right? So even though you have only the 2, it's still used to represent the unit step function. Any questions on this?
No.
Okay. Now, based on the unit step function and the shifted unit step functions, I'm going to introduce to you another type of function. It's called rectangular window functions. So the rectangular window functions, this is the functions, right? Is representations of the function or the graph of a window functions here. It's look like a window, isn't it? Right? In this rectangle, right? And therefore the name rectangular window functions. And the rectangular window function is denoted as u sub ab, right? So a is the left bound and b is the right bound. And the function is defined as follows. So u of sub a comma b of t is defined as u of t minus a minus u of t minus b. Okay, so that is how it's defined based on the shifted to unit step functions. And I want to note that this is u sub a minus comma b of t. So this is the rectangular window functions. Okay. And in terms of piecewise defined functions, this is denoted as 0. Right, so the function is equal to 0 when t is less than a. The function is equal to 1 when t is between a and b. And 0 as well when t is greater than b. Okay. And I'm going to show you where I get this piecewise defined functions later in example 2. Okay, but for now, bear with me here. Based on the look of the graph, you can write down the piecewise defined function that way. Okay. Another way to represent this piecewise function is that, so instead of 2, 0 here, what I'm going to write is I have the piecewise defined functions of 1 when t is between a and b, and 0 otherwise. So another way to represent it, or to write the piecewise defined function, or to write the rectangular window functions. Again, I'm going to show you where this is coming from. Okay. Let's consider the following functions. You have u sub pi of t minus u sub 2 pi of t. And this is going to be the window functions. Even though in the window functions, you start out with u sub a comma b of t, eventually you're going to see that how it is written. But for now, this is the formula. I'm going to derive the piecewise defined function and then give you the final notations on that. So the function is going to be so u sub pi of t, this can be written as u of t minus pi, and u sub 2 pi of t, this can be written as u of t minus 2 pi. Okay. So this is the shifted to unit step functions. So the functions, piecewise defined function is of the form 0, as t is less than pi, is equal to 1 when t is greater than pi. Okay. And for u of t minus 2, you have 0 when t is less than 2 pi, and 1 when t is greater than 2 pi. Okay. Now, when you put this on the plot, in the graph, you have t equal to pi, t equal to 2 pi, right? So pi here, and 2 pi here, and then 0 is here at the origin. So when you look at this, you have 3 different intervals, right? You have the interval, let's say t less than pi. So from here to here is one interval, t less than pi. You have the interval from pi to 2 pi. And you have one more interval here when t is greater than 2 pi. So that is the 3 intervals that you need to consider, even though that you only have 2 intervals when you write down the piecewise defined functions. Okay, but because you have 2 functions simultaneously appear in the equations, so you have to combine them somehow. You have to do manipulations to combine them somehow. Okay, so you, based on this information and based on the 3 intervals that you get, you rewrite this piecewise defined function instead of in terms of 2 intervals, you have to write it into terms of 3 intervals. So the functions, when t is less than pi, so in this interval, the function is equal to 0. And t is less than pi. Now, in terms of inside the interval between pi and 2 pi, what is the function going to be? So the function is going to be 1 because t is greater than pi. So in the interval between pi and 2 pi, the function is 1. And of course, in the interval when t is greater than 2 pi, the function is also equal to 1. You follow how I get this 3 intervals and how I get the functions. Any questions on that?
I don't think so.
Okay, so so for this function, let's say for this function, right, the function is equal to 0, right, when t is less than pi. You're okay with that so far?
Yep.
Okay.
Yep.
Now the function is equal to 1 when t is greater than pi. So let's say this one is 1. You're okay with that? So the function in the interval between pi and 2 pi, the function is 1. And when t is greater than 2 pi, the function is equal to 1 as well. You okay with that?
Yep.
Okay, so that's why you have this information. Right? Now for the second functions, for this second piecewise defined function, you also need to break it down into 3 different intervals. So when t is less than pi, when t is between pi and 2 pi, and when t is greater than 2 pi. Okay, so when t is less than 2 pi, the function is equal to 0, so you can draw here, so less than 2 pi. So in the interval of t less than pi, the function is 0. Right? In the interval between pi and 2 pi, the function is also equal to 0. And when t is greater than 2 pi, the function is equal to 1. Okay, so that's why you have 1 here. Now for the 3 different intervals, you can do calculations now. So 0 minus 0, 1 minus 0, and 1 minus 1. So for the 3 interval, when t is less than pi, when t is between pi and 2 pi, and when t is greater than 2 pi. Right. So 0 minus 0 give you 0. 1 minus 0 give you 1. And 1 minus 1 give you 0. Okay, so that's how you get the window functions. Okay, and is similar to what we have right here. Right? So I just show you where the windows where the piecewise defined function of the window function is coming from. Okay, for a in this case equal to pi, and b in this case is equal to 2 pi. But instead of writing like this, you can write this as 1 when t is between pi and 2 pi, and 0 otherwise. Okay, and this is the window function, so you can also write this as u sub pi comma 2 pi of t to illustrate that this is the rectangular window functions for a is equal to pi and b is equal to 2 pi. When you plot these functions, you should get the following. So this is 2 pi. The function is equal to 1 in the interval between pi and 2 pi. And the function is equal to 0 when t is less than pi, when t is greater than 2 pi. So that's a. So let me change this to dotted line. It's not really straight for some reason. Okay, but you get the idea. You get the idea. So that is the rectangular window functions. Any questions on this?
No.
No.
Good. You follow along? Yes.
Yeah. Do we have to do the full written out process every time, or since we've proven it, can we just assume?
That's a good question.
That function, we can just rewrite it as so.
So the answer is no. You don't have to go through this again. However, there's a lot of problem that you have to actually write down the details like this to arrive at the correct answer. So I just show you how to find the rectangular window functions, but you see later you have all the piecewise defined function, and it's not straightforward to just write out the answer. You have to do a little bit of manipulations to get the answer. But when you see a window function like this, you don't have to go over all the details again. I mean, for this functions, there's no way you can just look at it and you get the answer, right? You have to do a little bit of work on this. All right, so
it leads right into the example.
One more time.
That leads right into the example.
Right. So example 3, you have this piecewise defined functions. Right? I want to rewrite this function in terms of step functions and window functions. See what you get. So this function of this example is very similar to what we see here in example 1. The difference is that in example 1 you only have constant functions at every interval, but for this functions you have you have t squared over 10, which is a not constant functions. And you're going to follow what we see earlier in example 1, and you use in order. Okay, let me show you how that works. Right, so at 1 of t, you start with the function 3 right here, and in the interval of t less than 2, which is the interval between 0 and 2, you can say that. So 3 of ut. Okay, and then for the second functions, you should include the information of the first function, that is 3 times u of t plus minus 2 times u of t minus 2. Again, how I can get negative 2, so this is negative 2 is actually of the new functions minus the old functions. For the new function is 1, the old function is 3, so that's why you get negative 2. Now f3 of t is 3 times u of t minus 2 times u of t minus 2. The next function is t, and the interval start at 5. So you get u of t minus 5. So what is the coefficients here? The new function is t, and the old function is 1, so t minus 1. So you add this with t minus 1. So hopefully at this point you see where all of this is coming from. All right. And that is the third functions. Now for the fourth function, which is the combinations of all of the functions that we did in F1, F2, and F3. So F4 should include 3 times u of t minus 2 times u of t minus 2 plus t minus 1 times u of t minus 5 plus the last interval is t greater than 8 or t minus 8 here. You shift it to the right by 8 units. And for the coefficients, you have new function minus the old function. So new function is t squared over 10 minus the old function is t. So here you have t squared over 10 minus t. So that is the functions that's used to represent the piecewise defined functions that you have here. Okay. Then f of t is equal to 3 times u of t minus 2 times u of t minus 2 plus t minus 1 times u of t minus 5 plus t over 10 minus t times u of t minus 8. Okay, any questions?
No.
Okay, good. So this function is represented in terms of step functions. Now, in terms of the window functions, it's going to be much similar. Right? So you just take a look at 3, 1, t squared over 10, and multiply with the corresponding window functions. Okay. So in terms of the window functions, we get that f of t equal to 3 times u sub 0, 2t. Okay, to represent the first interval because you always start at 0. Right? Again, the idea because you are dealing with the time interval, so time is greater than 0, greater than or equal to 0. Now the next one is 1. So 1 times u sub 2, 5 of t. Why is 1? Because of the functions 1 here, right? And the interval is between 2 and 5, so that's why you have the window function like that. The next one is t plus t times u sub 5, 8 t. Okay. And the last one is t squared over 10, okay, times u of t minus 8. Because you no longer have the right hand bound, right? You only have the left hand bound. Only the left bound, so, or t is greater than 8 like this, or less than infinity. So therefore, you cannot represent the last function as a window function. You are only able to present the last function in terms of step functions. Okay, so in terms of the window function, this is what you get for the function that you are given. Any questions? You okay with this?
Yeah, not too bad.
Okay. Now you can go back and forth between these two functions, between window functions and the shifted unit step functions. Okay, because remember the formula for the rectangular window function is u of t minus a minus u of t minus b. Right? If you expand this window function and combine like terms, you should be able to go back to this functions right here that you get in terms of the shifted unit step function. All right. Now, of course, you want to apply Laplace transform on this functions. And Laplace transform on step function, these are the formula. So you can use this table right here, or you can use the Laplace transform table that I give you. So for the unit step functions, you go to the Laplace transform table. You get this. This is the unit step functions right here, or shifted unit step functions. And this is the Laplace transform. So I'm going to go back and forth between the two here. This is just the step functions, or just this is the unit step function, and the function is equal to 1. You have the Laplace transform of 1 is 1 over s. So this is the example that we consider in lecture 14 already. This is unit step function multiplied with the shifted functions. So this is the Laplace transform. If you have a shifted unit step function multiplied with the function g of t, there's no shift on that function g of t. When you do Laplace transform, later on you have to shift it back to the left for the function g of t. So the plus c here indicate that you should have to shift it back by c units, or shift it to the left by c units. Okay. In the exam, when I ask you this type of questions, I'm going to give you in the test the table of Laplace transform, so you don't have to look on Google or anywhere else. Okay. So let's start with evaluating the functions right here, t minus 1 times u of t minus 1. And we're going to use this formula right here to find the Laplace transform. Okay. And because u of t minus c times f of t minus c, they are shifted to the right by c unit, in this case by 1 unit, so you have c is equal to 1. So here c is equal to 1, then the Laplace transform is, so Laplace transform of t minus 1 times u of t minus 1 is equal to e to the negative 1 times s times Laplace transform. So capital F of s indicates that this is Laplace transform of the function t, of the function f of t. In this case, the function f of t is just t. Do you understand why I get t only? Because f...
1 represents the shift, right?
Exactly, because 1 represents the shift. So the function, the original function, or the function f of t is only equal to t, right? Then 1 represents the shift. So that's why you have e to the negative s times Laplace transform of t. Okay? And you go to Laplace transform table, and Laplace transform of t, so let me get rid of this. This is what you're looking for right here, number 16. So in this case, n is equal to 1. So Laplace transform of t to the first power is 1 factorial over s to the power 1 plus 1. So together, Laplace transform of t is equal to 1 over s squared. So this is e to the negative s times 1 over s squared. Right, so that is the answer, or you can write e to the negative s divided by s squared. Any questions on this?
Not yet.
Okay, good. Now we're going to move on to example 5. You have t times u of t minus 2. So the shift now is to the right by 2 units, right? So c is equal to 2. So here, c is equal to 2. Then the Laplace transform of t times u of t minus 2 is going to be e to the negative 2s, again c is equal to 2, times the Laplace transform of g of t plus 2. So c is equal to 2 in this case. And g of t is equal to t, or g of t plus 2 is equal to t plus 2. Okay, and that is the Laplace transform equal to e to the negative 2s times Laplace transform of t plus 2. Okay. Or this is e to the negative 2s times Laplace transform of t plus 2 times Laplace transform of 1. Okay. Laplace transform of t, you see earlier already over here, is 1 over s squared plus 2 times Laplace transform of 1. Go back here and you get here. Laplace transform of 1 is 1 over s